Welcome students. Now we are going to discuss about the most interesting part, that is formations of disaccharides. The very first thing, that is sucrose. Now let's first understand what exactly are disaccharides. Then disaccharides are those compounds which on hydrolysis give two monomeric units. They might be same or they might be different. Let's understand some examples. Now, first example which we have is sucrose, which is obtained by adding glucose and fructose. The molecular formula being C12H22O11. Next, let's take an example of maltose, obtained by adding glucose plus glucose. Again the molecular formula C12H22O11. Next, cellobiose, by adding glucose plus glucose once again, but molecular formula once again the same. And finally, that is lactose, which is nothing but galactose and glucose having the same molecular formula yet again. So the next point after the molecular formula, what we can write down is that in disaccharides, the anomeric carbon of one monosaccharide gets bonded to another carbon atom of another monosaccharide through an oxygen atom. Let's see how. Suppose if we take two sugar molecules, that is two sugar monosaccharides, and now both of these sugars are combined together. In this case, what would happen is a water molecule is lost. So what we are remaining is, we have sugars, but now in between these two sugars there is only one single oxygen which is present. So we would get a bond, that is sugar oxygen sugar bond, which would be called as an glycosidic linkage or ether linkage. Moving further, we also need to know a very important point. I have a monosaccharide right now over here. In this case, if I say onto an anomeric carbon, if I have a directly attached OH group, then it will give me a positive test with Tollens reagent, thus giving me a cyclic form, getting converted into a free carbonyl group. And we would say these type of monosaccharides or sugars as reducing sugars. But now let's suppose in the second case, if I say this OH was now substituted, then it would not react with Tollens reagent, and now this sugar would be called as a non-reducing sugar, whereas the oxygen sugar bond would be called as a glycosidic linkage or a glycosidic bond. Now finally, let's understand the actual structure of sucrose molecule, which is also known as cane sugar or common table sugar. Now, sucrose is prepared by C1 of alpha D glucopyranose and C2 of beta D fructofuranose. We have already discussed about the structures of alpha D glucopyranose. The structure was this. Also, we discussed about the structure of beta D fructofuranose, wherein the structure was something like this. Now what happens is, we need to make a bond between the first carbon atom and the second carbon atom of glucose and fructose respectively. Let's do this. What would happen? They would combine together and they would lose down a water molecule. And if this happens, we are bound to get a glycosidic linkage in this case. And now, if we observe this glycosidic linkage very carefully, the anomeric carbons, that is the first and the second carbons, are not binded to OH groups. That means these groups or these carbons are no longer giving me a positive Tollens reagent test. That means this sugar is a non-reducing sugar. So sucrose is an example of non-reducing sugar. Let's move further and now discuss some crucial points with respect to sucrose. First thing, sucrose on hydrolysis gives equimolar proportions of dextrorotatory glucose and levorotatory fructose. But now, sucrose is actually a dextrorotatory compound, but once it is hydrolyzed, it gets converted into a levorotatory compound because the levorotation of fructose is negative 92.4, whereas the dextrorotation of glucose is positive 52.5. So levo always dominates, and because of this inversion in its rotation, it is also referred as invert sugar. So these were some important points of sucrose and the structure of sucrose, a very important question. I hope this question is clear in your minds. Meet you in the next module. Till then, thank you, students.